Now you know one method of charging, which is charging by friction. But what if you say this is too much work, my hands are aching with all this rubbing? And you say, isn't there an easier way to get charges onto things or off of them? There is. If you pick up a conductor, right, you can do something else. I want you to watch this. And I'm not going to explain what's happening, and I want you to think about what you think is happening over here. So this is a conductor. There's a glass below, so when I'm holding it, I'm not really touching the conductor. It's an insulated glass and a conducting ball on top. Now this is something, let's talk about this, but if I touch this, nothing happens. And you're wondering, why is that worth mentioning? It's worth mentioning because now I want you to put your focus onto something that's there over here, which has a name, which you will learn about at the end of next chapter. But as of now, I'm going to switch this device on and let's see what happens. Okay. Clearly, this has something going on in it. There are still some pieces of paper stuck onto it. So something happens inside this, which we'll talk about much later. But what's happening on the outside as of now is that I shouldn't go too close. It's charged and there'll be a spark. To confirm that, like I can do a safer experiment. If I take this over here, yeah. I think I shouldn't do that. I should do this. Yeah, I think you can see it's sparking off. So I don't know how many ways I need to convince you about something that's happening over here. So clearly this ball over here is charged, right? I don't think I need to convince you anymore. Now watch what happens. I'm going to touch this conductor to that. Yeah, that's all I did. There's no rubbing involved. I'm going to switch it off because I'm a little worried about sitting alongside with that one. So now something could have happened here. I don't know what's going to happen, but now I'm going to touch this with that. Oh yeah. So do you observe something over here? Those two pieces began to repel each other the moment I touched it with this. And I think you can see it again if I do this, yeah. Now, after you observe this, right, you saw a whole sequence of things. I took this and touched it, nothing happened, touched it with that, and then brought it here, then something happened. Spend some time thinking about what exactly happened over here and come back. Talk to your friends about it, Get enough people convinced, disagree with them, then come back with what you think is happening, and then we'll talk about what we think is happening. So did you think about it? Now let's watch a slight variation of that experiment, right? So if I switch this on again, just for a little bit, let it get charged a little bit, not too much. And then if I touch this, right? Now if I bring this over here, can you observe that nothing really is happening? But when I did it with this, it happened. So what's different between these two? It is that this is a conductor and this is not. And what's the deeper way to say that same difference, right? How are the electrons arranged in a conductor and how is that different from the way they are arranged in an insulator? Can you remember that? Do you remember that in an insulator, each atom holds on to its electrons very dearly, right? So the electrons know exactly which atom of this glass they belong to and they stay there. But in the case of a conductor, you know that many electrons from the valence shell, which is the outermost shell, end up roaming around all over the conductor. They can move around wherever they want to. It's called the electron C model of conduction. So now that you know that this is different from that in that way, which is that the electrons here can move around, and that's true for that as well, then can you now again spend some time thinking about what could be happening when we touch this over here and then touch it to this, because you observe that this is also entirely a conductor. So did you actually take some time to think about this? You didn't, did you? You just click the next button and you want me to explain it. Fine, let's do it. It's my job and I get paid for it. So when you take this ball, you know that electrons inside can flow. We call it the electron C model, right? But let's confirm that, right? What you already have in mind. So if you took this ball and you saw it to be neutral, then you know that some electrons can be flowing. And then when we touched it to the charged, let's call it a ball over here, it actually could be positively or negatively charged. It doesn't really matter. This is neutral. Let's imagine it's negatively charged. The moment you're touching it, what you're doing is that observing that because there's a sea of electrons over there, let's only look at the electrons that are in excess of the protons, because that's what we care about. Those negative electrons are now finding a new place to go to, and they've been repelling each other now a little bit because there are more of them. So they find this new place and start flowing into this. Now this also has some extra electrons. Let's give a number. Let's say this one has about 2.5 microcoulombs of charge, 2 microcoulombs of charge, and let's say that once it's been touched, 0.5 of it flew or flowed into this. Now if you take this out, no charges are flowing back again, they can't anymore because there's air in the middle. So now you've taken out, let's say 0.5 microcoulomb into this, then how much is remaining over there? Yeah, law of conservation of charge. So 1.5 microcoulomb remains over there. But what you have done is that you've taken a neutral conductor. Just by touching, no rubbing, you made this charged. But if you're not convinced, if you want to see it in some way, right, we have a hack to kind of visualize the fact that this has some extra electrons on it. Now, this is the device we're going to use. I'm calling it a device, it's actually just one wire and some couple of very, very light pieces of metal hanging there. Now, given that this is a conductor, right, and those two are conductors as well, what do you expect will happen if I take this and touch that tip with this conductor? There are extra electrons here, they're repelling, they want some place to get out. So the moment you touch them, if this were charged, we can expect that the charges would flow down, reach those two foils, and leaves we call them because they're very light. And they're so light that if the two are similarly charged, if both are negatively charged, you can expect them to start repelling each other. And that's a way to see the fact that this is charged. Let's do that now. And that's what we observe. So this now takes us away from our realm of just imagining electrons flowing there to seeing this thing really, like we are actually watching what's happening over here, and we know that that repulsion doesn't make sense if this was not charged. Now, of course, you can ask me, are we sure it's negatively charged? Not really. It could have been, the whole thing could have been done with positive charges and this would have still worked. Because positive charges just means electrons are flowing in the opposite direction and both of them were positively charged. Now this device, right, which helps us identify whether what we're touching it with is charged or not, is called an electroscope, typically based on what leaf we use there. It's called, in books I think I've read about gold leaf electroscopes. This one looks like it's silver. Which one is it?
It's aluminum.
Yeah, it's an aluminum leaf electroscope. So, but it still does the job. So we know that this was charged, and we know the electrons flowed, and now, right now it's charged. Now watch what happens if we touch it. It comes back to position. Think about what's happening over there.